We're running out of time, so let's quickly talk about sound waves. Sound is a longitudinal wave, and by that we mean that the motion can be represented with a slinky. If I take a slinky and make a bunch of disturbances, a bunch of pulses, what I end up with is some compressed regions where the slinky is bunched and some rarefied regions where it's spread out. I can do that with sound with a tube that has a speaker in the end of it. That speaker diaphragm is pushed out and in, out and in. If instead of some rock song, I have a pure tone, a single frequency. I'm trying. Okay? That diaphragm is going to go back and forth with the same period every single time. And that's going to create some compressed regions when the diaphragm goes out, and it's going to form some rarefied regions when it comes back. And those will move out like this. Now you can follow a wave front, a region where it's compressed, as it moves down the tube. Now that's what we were talking about last day when we drew sound as a bunch of lines. Those were the compressed regions that move at the speed of sound. That's the pulse right there. But if I look at a single molecule, it doesn't go very far from equilibrium. Okay? Not very far at all. So we get something like that. And then those disturbances push your eardrum in and out. Now, I have here a speaker, a bell, if you will, and also a microphone to pick up that sound. If I open the bell jar, can you hear it in front? Okay. Now, on the oscilloscope here, we are registering what's on the microphone. Essentially what sound is being picked up there. When I talk louder, it picks up that. Now, what we're going to do is we're going to pump the air out of this bell jar. And that'll take it off the scale for a while, but then it will auto-correct and bring it back on. We got plenty of time. There we go, here it's coming. Notice that the amplitude is much smaller, except when I talk. If we continue to pump the air out of this thing, that'll get flatter and flatter and flatter. The message here is that in outer space, no one can hear you scream. Okay? We need that medium, that air, to... Hey folks, you're still paying me for 2 more minutes. Now, as that sound wave goes down, you're going to have regions of high pressure and low pressure, and then atmospheric pressure. Now, it turns out, and this I find remarkable, that at the high pressure regions for normal sound, it's only like 0.03 pascals above atmospheric. Now, you remember that in everyday life when you're walking around, you are surrounded by air that's at 1 atmosphere. And 1 atmosphere is 101,325 pascals, where a pascal is 1 Newton for each meter squared. That's a fairly large pressure. And yet, your eardrums, healthy ones like you have, can detect little tiny fluctuations in pressure that are only 0.03 pascals. Compared to that, that's like nothing. Your ear is a very, very, very impressive instrument. Don't go to rock concerts. Okay? Okay, let's call it quits.